Here's a video of me pitching. Before I begin my motion, I grip the type of pitch that I want to throw and conceal it in my glove. As I extend my leg and kick it high, I slowly begin to shift my body weight forward. When I am ready to throw the ball, I push off my back foot and launch myself towards home plate. My arm breaks away from my glove and makes a circular motion with the ball until I release it in front of my body. My arm extends across my torso and I finish, balanced on my front foot. I commonly throw 3 different pitches, each having a unique grip. The fastball, the changeup, and the curveball. Given the fact that the batter has less than 300 milliseconds to identify the pitch and begin his swing, varying the spin, speed, and location of the pitch can make this task very difficult for the hitter. The purpose of the fastball is to throw the ball with exceptional velocity in order to test the reaction time of the hitter. The spin of a fastball is directly backwards, although certain factors may affect the spin as it approaches the plate. Although the ball does slow down as it travels due to air resistance, we can calculate the average velocity using the equation velocity equals distance over time. The pitcher's mound is 60.5 feet away from home plate, and it takes the ball approximately 15 frames to reach the catcher's mitt from release point. Since the camera is recording at 30 frames per second, we can easily conclude that it takes the ball about half a second to reach home plate. Since pitching velocity is usually measured in miles per hour, we have to use dimensional analysis to fix our units. By multiplying 60.5 feet by 1 mile by 3,600 divided by 0.5 seconds, 5,280 feet, and 1 hour, with feet and seconds canceling out, the result is 82.5 miles per hour. Pitchers generate tremendous rotational velocity, which tests the limits of what the human arm can tolerate. As I prepare to release the ball, it takes my arm 2 frames on a 30 FPS camera to rotate through a 180-degree arc, or pi radians. By dividing pi by 0.07 seconds, which is the amount of time in seconds, we get the answer 44.88 radians per second. If my arm were to continue in this motion at the same velocity for an entire second, it would rotate through over 7 full circles. This amazing generation of rotational velocity is one of the reasons why elbow injuries are so common among pitchers. Here's a video of my brother Andy hitting some baseballs. Notice how as he stands in the batter's box, he is in a balanced, athletic stance in preparation to hit the ball. His eyes stay focused on the ball from when it leaves the pitcher's hand all the way until it makes contact with the bat. As he makes contact with the ball, he drives his arms downward and through the center of his body. His hips fire open, generating an incredible amount of torque. Notice how he stays balanced throughout the entire swing. His bat speed can be determined by the equation V equals the square root of 2e over little m plus e squared times big M. Little m is the mass of the bat, big M is the mass of the player, and E is a normalization constant approximately equal to the total energy produced by the muscles. The constant, E, is taken as equal to 1/9, which is in accord with the observation that the maximum energy of the bat and the player are roughly equal. Using this relation, for a given total energy, E, we determine the variation of V with M for a batter's given weight, big M. Since we can't really calculate the energy put out by the muscles, it's more of a theoretical formula. However, we can assume that the energy put out by the muscles is proportional to the weight of the player. The law of conservation of momentum is extremely important when it comes to hitting. The conservation of momentum can be tested by using the formula mass of bat before collision times velocity of bat before collision plus mass of ball before collision times velocity of ball before collision equals mass of bat after collision times velocity of bat after collision plus mass of ball after collision times velocity of ball after collision. At the Little League, high school, and college level, there have been a number of injuries due to extremely hard batted balls. To solve this, baseball ruling committees adopted the BB course standard, which decreased the velocity of the ball coming off the bat relative to the speed of the ball before contact. The coefficient of restitution, or CORE, is the ratio of the velocity of a ball rebounding from a hard, immovable surface. It can be calculated by dividing the velocity of the ball minus the velocity of the bat after the collision by the velocity of the ball minus the velocity of the bat before the collision. Therefore, the smaller COR, or core coefficient of restitution, the softer the ball comes off the bat. The ball exit speed can be calculated by adding 1 to the COR multiplied by the bat speed and adding the COR times the speed of the pitch. Andy's bat speed is approximately 80 miles an hour, and in this batting practice session, the ball is coming in at around 60 miles per hour. Using an average COR value of 0.2, the calculated ball exit velocity is 108 miles per hour.